Today we are going to talk about exponential functions. And the first example that comes to my mind is just the function 2 to the power of x. Later on we can change that number 2 to other numbers, but let's think about this one for a little bit first. I want to look at what happens to the number 2 when it is put to the power of different values of x. And of course, this independent variable x here can be any real number. But just for simplicity, let's look at some natural numbers, 2 to the power of 1, 2 to the power of 2, and so on. And I do think it's important to point out when we're teaching this that this is a choice for simplicity, because a lot of students, when you say the word number, they do think of numbers as just 1, 2, 3, 4, and so on, and not really the concept of real numbers, which involves all the rational numbers and all the irrational numbers, the positives, the negatives, and all of that more complicated stuff. So when the teacher consistently insists that other numbers exist, rationals, irrationals, and whatnot, but whenever something new is being taught, and now let's put some numbers in here, and then the teacher herself just goes 1, 2, 3, 4, I think that kind of reinforces the confusion for the students that 1, 2, 3, 4, like natural numbers, are the only ones that are actually numbers. So anyway, I just like to point out that I'm putting 1, 2, 3, 4, not because they are the only numbers that exist, but just because they are simple numbers to deal with. I know that f of 1 needs to be 2, f of 2 is 4, f of 3 is 8, because my function is 2 to the power of x. So let's just, as examples, put these 4 points on the graph. Please notice that what I am doing here is a sketch. It is not a drawing. So let's take a moment to talk again about this distinction between sketch and drawing, because the sketch doesn't require to have a proper scale on the axis. You see that my 4 doesn't quite look twice as big as my 2, and my 8 definitely doesn't look twice as big as my 4, and that is perfectly fine. This is a sketch that I'm doing, and this is why sketching instead of drawing is good. Because if I was constrained to keeping a proper scale here, then I wouldn't be able to see anything useful in this picture. Notice that I have already not been able to put the 4th number in my sketch because it was going to go up too much and it wouldn't fit here. And this kind of problem would be even worse if I was trying to keep my axis in a scale. So before anything else, this is the first important observation about exponential functions. They grow really fast. So if I can't try to put any more bigger numbers on my sketch for this reason, let's just try to go the other way and put some smaller numbers. So 2 to the power of 0 is equal to 1, 2 to the power of negative 1 is a half, and I've put those 2 points on the sketch. I could keep going. But what I do want to point out here is that exponential functions is not specifically one of the topics that I think students tend to consider the most difficult ones. But when they do find it difficult, I think this follows the pattern of every other difficulty that people face. It's not exactly that the thing in itself is difficult, but it's that it relies on another piece of knowledge that you have seen before, but maybe you didn't learn it as well as you thought. And in this case, I'm talking, of course, about negative exponents. So here's the number negative 3 as another example, right? F of negative 3 is 2 to the power of negative 3 by the definition of the function that we are studying. But this, because it's a negative exponent, is equal to 1 over 2 to the power 3, which is 1 over 8, which is that point over there. So the consequence of this is going to be the interesting shape on the other side of the picture. Because this side of the picture, we've already mentioned that it's interesting because it grows really fast. But what is happening on that side? It is getting smaller and smaller, because as this number gets smaller, then this exponent here gets bigger, this denominator gets bigger, which means that the fraction gets smaller. So the right side of the sketch is growing very fast, but the left side is getting smaller, always as a positive number. It's going to be a very small number, like 1 over 8, 1 over 16, 1 over 32, and here I am again inadvertently reinforcing the idea that numbers are only the integers. I am so sorry about that. So here's a different number, okay? 2 to the power of negative 100 pi, an irrational exponent. There you go. This is a very small number, but it is a positive number. So here is maybe a new vocabulary word that I want you to learn. This depends on what other functions you've studied before. But this behavior that we are describing that this function has on the left side of getting smaller and smaller but never passing zero, this has a name. This is called an asymptote. And this will not be a new word for you if you've seen rational functions before, because those also have asymptotes, although they're a completely different kind of function. But if you're studying this one first, so here is a new concept, a new word. An asymptote is a line, which in this case is the horizontal line, which is the horizontal axis of the coordinate plane. So an asymptote is a line that a given function is approaching. And this word approaching is very interesting because it doesn't have to actually get there. It just has to be going in that direction, which is exactly what is happening here. Okay, so an asymptote is a straight line that the function approaches when it is going to infinity. And I do like to phrase it in that sort of ambiguous way, like it is going to infinity, what is going to infinity? In this case, is the x that is going to negative infinity, right? But I like to be a little bit more vague than that, just to account for other types of asymptotes that exist. So this is one of the special types of functions that we have to study inside of our IB syllabus. And as usual for all the special functions, you know that when you are making sketches of them, you have to point out all the relevant features. Asymptote is definitely one of the relevant features, so we've already covered that. And the other ones include axis-intercepts and turning points. So we better talk about that too. The fact that the function never crosses zero is already telling us that it does not have any x-intercepts. But we should also talk about the y-intercept. And this one is interesting because for any function, the y-intercept will be f of 0, which in this case is 2 to the power of 0, which is equal to 1. But not only that, even if it wasn't the number 2, if it was a different base that we were working with, any number to the power of 0 is going to be equal to 1. So that is a common fact for any exponential function that you're studying, not just 2 to the power of x, that the y-intercept is always at y equals 1. Well, and turning points, we're just mentioning them because we have to mention such things. But of course, it doesn't have any turning points, right? This function is always getting bigger, 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 bigger. And a turning point is when something that was increasing becomes decreasing, or vice versa. This kind of function doesn't do that, so I'm just going to write down that it doesn't have any turning points. And to be really complete, I should also mention that it doesn't have a vertical asymptote, because I did mention here that it has a horizontal asymptote. So you could guess that such a thing as a vertical asymptote also exists, right? And in fact, if you have already studied rational functions, you know that it does exist, and the rational function has both, but this one doesn't. So as important as saying that it has a horizontal asymptote, it's also to say that it doesn't have a vertical asymptote. And it's important to mention this because of the fact that we've already said it grows really, really fast. And a lot of times, instead of making sketches yourself, you are going to be looking at plots that your calculator does for you. And visually, it is going to look like it has a vertical asymptote. This is what that kind of thing looks like, especially depending on what zoom you use. Like if you're really, really close, you're going to see the curve like we see in our sketch here. But if you zoom out, you put a bigger window, then it's really going to look like it's vertical. It's not vertical in reality, okay? It's just going really, really fast. And when I say really, really fast, that is really, really fast. It is so fast that by looking at your calculator, you may think that it has a vertical asymptote, but it's important for you to know that it does not. Okay, so now let's explore what happens when we change the base of our exponential function. Here is a second one that I'm going to sketch in green. It's 3 to the power of x. We've already mentioned that anything to the power of 0 is 1, and that means that the y-intercept of the function is always 1. So that's not going to change. But what is g of 1? Well, 3 to the power of 1 is 3, so instead of 2, it's going to be 3. And every number in between has also gotten a little bit bigger than it was before on f, right? For example, what happens when x is equal to a half? Well, f of a half is 2 to the power of 1/2, which, you know, is the square root of 2. The square root of 3 is bigger than the square root of 2, so there you go. Everything in the green function is bigger than the corresponding point in the red function. And now not even g of 3 I'm able to fit in my sketch, right? It grows really, really fast. But what happens on the left side? That's interesting to think about. G of -1 is 3 to the power of -1, which is 1 over 3. And 1 over 3 is actually a smaller number than 1 over 2. So while on the right side, the bigger base made the function be bigger than the other one, on the left side, the bigger base meant that the new function is actually smaller than the original function. All of the other things that we said about it are still going to be true. So in particular, it has to keep getting smaller, and it can't cross the 0 because it also has that same horizontal asymptote. So the thing that I'm trying to sketch here in green is kind of squished in a very small space. It has to be between the red function and the black horizontal axis. I'm not going to make a third sketch with an even bigger base, but of course you could do that. You could do the same thing in sketch 4 to the power of x, or you can just take any other number that is bigger than 3, such as pi to the power of x, for example, because remember, natural numbers are not the only numbers that exist, and it would look exactly the same. It would go a little bit higher than the green one on this side and a little bit lower than it on the other side, but importantly, they would still cross at the point 0, 1. What I want to do instead is not get a bigger and bigger base, but I want to go to the other side and get a smaller base. So if I was going to say 1 to the power of x, that would be a really stupid function because 1 to the power of anything is just 1. So I would be talking about a constant function which was a horizontal line y equals 1. We don't usually consider that as an exponential function, even though algebraically it looks the same as the other ones, but it doesn't have any of the same features as you expect exponential functions to have, so I'm just going to take that out of there. What I do want to look at is this one, a half to the power of x. And again, you kind of really need to be comfortable with your rules of exponents in order to make sense of all of this content. But a half to the power of x is just 1 over 2 to the power of x. And yet another way to say this, another thing that this is equal to, we can again use the negative exponent. This is 2 to the power of -x. So when you look at these two things, what you realize is that if the base is a half instead of being 2, then this new function is just a horizontal reflection of the red one. That one is also going through the point 0, 1, by the way. And if you're not new to this channel, you probably already know that graphical transformations of functions is one of my favorite things to talk about. Doing an operation such as minus to the independent variable, which is x, is always going to result in a horizontal transformation, which in this case is reflection because of the negative sign. And then when instead of that, you do an operation to the function itself, not to its independent variable, that results in a vertical transformation. But we're going to talk more about those in a minute in this video. What I wanted to point out is that for exponential functions, it turns out that you don't have to work with horizontal transformations at all, which is good because vertical transformations are easier. Well, the first observation is that you don't have to worry about horizontal reflections because you might as well just work with a different exponential function that has the inverse base. So if you want to take 2 to the power of x and make a horizontal reflection. You don't have to do that. You just change the 2 to a 1 over 2. That is the same thing as the blue function that we drew over there. So that's another really interesting thing to put on this list. When the base of the exponential function is a number bigger than 1, like the red one and the green one, then that makes an increasing function. But when the base of the exponential is instead a number between 0 and 1, like a half in the example of the blue function, then that makes a decreasing function. That can make it sound a little bit strange if you think that the word grow implies that it's an increasing function. But let's just put that between quotes and interpret that you can be growing to the right or growing to the left, okay? You grow really, really fast to one side, and then on the other side, that's where you have the horizontal asymptote. Look, the red and the green functions are growing on the right, but having a horizontal asymptote on the left. And the blue function is doing the opposite. It's growing really fast on the left, but having a horizontal asymptote on the right. So why did I say that you wouldn't have to worry about any of the horizontal transformations? I've already talked about reflection. Let's talk about the other ones. So how about a horizontal translation like f of x plus 3? Why don't I have to do that? Remember, f of x is my red function, 2 to the power of x. So that f of x plus 3 is 2 to the power of x plus 3. And again, using your rules of exponents, you know that this is just 2 to the power of x times 2 to the 3, which is 8. And now that addition has become a multiplication, but it's not a multiplication on the independent variable x. It's a multiplication on the function itself, which is a vertical transformation, not a horizontal one. And you can do something similar in the case of horizontal stretches when you multiply the independent variable by a number, which in the case of this function just makes it 2 to the power of 5x. And then using a different rule of exponents, you find that you are actually just dealing with a different exponential function because the base has changed. The base is now 32 instead of being 2. But that's it. So you don't have to worry about dealing with horizontal transformations. Vertical transformations, on the other hand, are very important to deal with in the context of exponential functions. For example, here is the function f of x equals 2 to the power of x. Again, I've removed all the individual points that I had marked before because that's irrelevant really. All that really matters is that you know the basic shape of an exponential function and its relevant features. So you have to sketch it with a horizontal asymptote and with the proper y-intercept in place, and basically looking like it grows really, really fast, but you don't have to put any individual points on it other than that. Anyway, now I want to make a vertical stretch. I am multiplying not the independent variable x, but I am multiplying the function itself by 3. And this is a common point of confusion because a lot of students at this point say, well, isn't that just the function 6 to the power of x because 3 times 2 is 6? Well, no, of course not. It isn't because order of operations. This is a product and this is a power. So powers always happen before products. That is the order of operations. So you can't just multiply 3 times 2 as if there wasn't an x there waiting to be powered first. You know, the x has a preference. It has to go first because it's an exponent that is a power. So you can't just multiply the 3 by the 2, making it a 6. What you have to do instead is take the function itself, which is what we have here, and then multiply the whole thing by 3. So that is how graphic transformations work. You take every single point of the curve and then you multiply the value of that point by 3. So in particular, the y-intercept is one of those points. So it used to be at 1 times 3, it's going to go to 3. All of these points here are also going to become 3 times higher. So if you want, I guess you can single out one of the points, like the point 1, 2, and make it into the point 1, 6. I don't think that's strictly necessary. But anyway, here it is. But what you do have to pay attention to now is that these other points on the left are also going to be just multiplied by 3. And that makes a difference because while these points here are just big numbers that you are probably more used to dealing with, these here are very small numbers. They are getting really, really small. They are not zero, but they're very close to zero. And what happens to zero when you multiply it by 3? Well, nothing. It's still zero, right? So the numbers that are very close to zero, they are almost zero. It's not that nothing happens to them when you multiply them by 3, but almost nothing happens. So bottom line is the asymptote is not going to go anywhere. The asymptote was approaching zero. When I multiply by 3, I am approaching 0 times 3, so I am still approaching 0. You can sketch it a little bit above the original one like I did there just to make sure you can still see both, but just don't overdo it so that it looks then like the asymptote is someplace else, because it's not supposed to. It's supposed to still be a horizontal asymptote at 0. Okay, so now let's make a vertical translation. I'm taking the green function that I already had, 3 times 2 to the power of x, and now from that whole thing, I am subtracting 1. That is a vertical translation. It means that instead of stretching like I just did from the red to the green, I'm just going to take the green function and bring it down by 1 unit. Each point in the green function is going to go down by 1 unit. In particular, the 3 is going to become the 2, while the 6 is going to become a 5, which kind of shows why I don't like putting too many unnecessary points on my sketches, because I've had to move things around there a little bit to make it fit. But anyway, the interesting thing is what's going to happen to the asymptote, because all of those points towards the end over there, they are very close to 0. So when I subtract 1 from them, they are going to be close to -1. And that is still going to be looking almost like a horizontal line because that's an asymptote, but that line is not going to be y equals 0 anymore. So that is going to change not the fact that it has a horizontal asymptote, but it's going to change what the horizontal asymptote is, which is now the line y equals -1. It has also apparently changed one of the basic facts about exponential functions that we had mentioned before. We had said that it doesn't have an x-intercept, and this one does. Here is an x-intercept, but that's okay. We were breaking the rules before that when the y-intercept became 3 instead of 1. The thing is that the set of features that I was writing here did not include the graphic transformations, right? So the moment I started doing graphic transformations on it, those things started to change. So the y-intercept that used to always be at 1, well, no, not really. Now it's at 3 because I've made a transformation on it. And then, well, it doesn't have a horizontal x-intercept. Well, but what if I bring everything down? Then it's going to have a horizontal intercept. That is because of the graphic transformation. That's not because of the exponential function. Anyway, if you are making a sketch of this function for a question maybe, then it's important to point out the value of the x-intercept. This is how we find x-intercepts. We ask for what value of x is my function equal to 0. This is also not about exponential functions. This is a general fact about functions. This is how we find x-intercepts. But in this case, h of x is this function right here. So this is the equation that you want to solve. Well, let's go ahead and do a bunch of inverse operations here on both sides of the equation to see what happens in the end to the value of x. We start by adding 1 on both sides. Again, here, because of the order of operations, we do need to deal with the 3 first, so we're going to divide both sides by 3. And if you can't think of a number that when you put 2 to the power of that number, then the answer is 1 over 3, well, yeah, I can't either. That's what logarithms are for. And again, one more instance of sometimes you think a topic is difficult, but it's not really difficult. It's just because you haven't really learned the previous content as well as you thought you had. So this is exactly what logarithms are for. You have a variable that is in the exponent. You're trying to isolate that variable, so x is the log base 2 of a third. The other side of that coin is that if you're studying exponential functions for this first time, and then when you get to this point, you say, wait a minute, can't I use a logarithm to get that x out of there? That feels really good, right? When you have actually really learned well the previous content to the point that you recognize it in a completely different situation that you had no reason to suspect would be related. So moving on, there is one more vertical transformation that we still have to talk about, and that is the vertical reflection. What happens when you put the minus sign in front, not of the independent variable x, but of the whole function. And in this case, I'm using the function f. Okay, so I'm putting the minus in front of the 2 to the power of x, that is the red function. Again, this is a very common point of confusion because a lot of students look at this and think that they're looking at a new exponential function just with a base that is now the number -2. But that is not the case for the same reason as the 3 times 2 was not 6. Order of operations. Minus in front of something is a multiplication by the number -1. And power always happens before multiplication. So this is not -2 to the power of x. This is -2 to the power of x, which is a vertical reflection. I'm going to take every number on that red curve and take the negative of it. So since all of them were up here, they're now all going to be down here. So that's what the orange function is going to look like when you do that, right? You could say that it's upside down. It has been reflected in a mirror over here in the axis. And this leads me to a type of exercise that I really like. It goes like this. Here are two pictures of exponential functions. And based on all of these things that you already know about exponential functions, I want you to come up with values for A, B, and C. Well, it's going to be a different set of values for the blue and for the orange functions, of course, but a set of numbers for orange and a set of numbers for blue that could result in these functions. This is not an algebraic exercise. A lot of people look at this and ask me to give more points on the graphs so that they can plug in the numbers for the points in the expression there and then do calculations. That's not what this exercise is about. This exercise is about recognizing the shape of an exponential function, recognizing some graphic transformations that have been done on them. You do have some freedom in the choices of numbers here. Not complete freedom, of course, but because I'm not giving you any extra points, like for the base of the function b, there's really only one thing that I told you about the base, which is that if it's bigger than 1, then it makes an increasing function. And if it is between 0 and 1, it's going to make a decreasing function. So, but there's still a lot of numbers to choose from, right? So that is the point. You can choose a number if you have to, because numbers are not going to come out of any calculation. This is about recognizing the shape of the functions and the effect of the graphic transformations. I'm going to give the answers in a little bit, but try to do it by yourself first. And by the way, I did mention what happens with a base that is bigger than 1 and what happens with a base that is between 0 and 1. I did say that a base equals to 1 is not allowed because that would just make a horizontal line. Well, same goes for the base equals 0. That would also be like 0 to the power of x is always 0, which is not interesting. So that also doesn't count. But the thing is that negative bases also don't count, okay? I've mentioned here that this is not a negative base because this is a minus in front, not of the 2, but of the 2 to the power of x. But when I did that, it kind of implied that it would be okay if you put a parentheses here, so that now it's changed the order of operation and the base actually is -2 and then to the power of x. But this possibility actually does not exist, okay? Negative bases are not allowed because that would only work for very few numbers. You know about odd and even exponents, right? -2 to the power of 2 would be 4, and -2 to the power of 3 would be -8. That in itself wouldn't be a problem, but the problem is that most numbers are not natural numbers. Most numbers will be things like 1/2, which is, well, -2 to the power of 1/2 would be the square root of -2 because that's how fractional exponents work, right? Except you cannot take the square root of negative numbers, and that is why negative bases are not allowed in exponential functions. All of that said, have you figured out the answer to this exercise? Well, first of all, one of these functions is upside down and the other one is not. The orange one is above its horizontal asymptote, which is the normal way, but the blue function is below its horizontal asymptote, which means that it is upside down. So the blue function, I know for sure, one of the transformations that it has suffered has been a vertical reflection. So I know that for the blue, this number here is going to have to be a negative number. But let's do the orange first. So orange is not upside down, but it is a decreasing function. So because it is a decreasing function, it needs a base that is a number between 0 and 1. I'm going to go with 0.7 because why not? I told you that you would have some choice. And then instead of adding something like the plus c over there, I actually want to subtract something because the vertical translation here clearly has brought my orange function down, right? The horizontal asymptote is now at -2. So that's how much I want to subtract. There is still one thing to fix here, which is the fact that the y-intercept needs to be at 3, and f of 0 right now is not looking like 3. Right now, f of 0 is, this to the power of 0 is 1, so 1 minus 2 is -1. I want to put like a 5 here, because then when I put f of 0, 0.7 to the power of 0 is 1, 5 times 1 is 5, 5 minus 2 is 3, which is exactly the number that I wanted there. Now let's think about blue. I already said that it is upside down, so it needs a negative here. I also think it's pretty easy to see that it needs a +2 there in order to get the horizontal asymptote to that y equals 2 line over there. So blue is also a decreasing function. So you might think that you want a small base here, a number between 0 and 1. But let's be careful because it is a decreasing function because it's upside down. Before it got turned upside down, it was actually an increasing function. So this base should be a number that's bigger than 1. So I'm going to put 3 because why not? And now I only need to figure out this number here. And for that, I'm going to use the fact that my y-intercept needs to be at -1. So what is happening with f of 0? 3 to the 0 is 1. So f of 0 is minus a plus 2. That needs to be equal to -1, so I guess a needs to be 3. Yeah, that was a silly choice. It looks ugly with 2 3s there, but it's not wrong. Well, I hope you're still here because now that we've gotten all of that out of the way, we've said all of the basic things about exponential functions. We know a lot of things about what they look like. Now we can begin to talk about what that's for and why it's fun to have such functions to work with. It all has to do with the fact that they grow really fast. But we need to take a better look at this sentence, grow really fast, because it might not be the best description of what the exponential function is doing. Growing really fast is something that other functions can do. In fact, if you look at these lines, you can say that the green line grows slowly, the orange line grows faster, and the blue line grows really fast. This is all relative to each other, but if you want one that grows really, really fast, then you can just take another color and draw another line with a bigger slope. So that's clearly not exponential. So growing really fast is not a good enough sentence to describe exponential growth, because the growth of lines is constant. That's what the slope of the line is, and that's not what exponential functions do. So let's try saying that they grow faster and faster. So maybe it's not so much about speed, but acceleration. This is a little bit better, but again, it's not exclusive to exponential functions to grow faster and faster. In fact, if you take these functions, x to the power of whatever you want, they also grow faster and faster. In fact, the bigger the exponent that you put on that x, the bigger this acceleration is going to be. So these are also growing faster and faster, but they are definitely not exponential. So again, this is not a good enough description of exponential growth. to say that it grows faster and faster. So the third definition that I'm going to show you is actually the correct one. The rate of growth is directly proportional to the value of the function. This is extremely important because this is how you're going to recognize in a given real-life context whether you should think of exponential growth for that situation or not. Is the thing that you're studying growing in a speed that is proportional to how much of it you have right now? That is the defining characteristic of exponential functions. The rate of growth is directly proportional to the current value of the function. But it is kind of difficult for teachers to talk about this when they are first teaching exponential functions because there is sort of a taboo about talking about rate of growth of functions. It is an extremely useful concept, and it is kind of an intuitive concept for you because you know about the rate of growth of lines, you know about slope, and you can intuitively understand what I mean when I say that these functions are growing faster and faster. The rate of growth is increasing. Look, it was increasing just slowly here, but here it's increasing faster. Isn't that intuitive? So why can't we quantify that with a number to say the rate of growth is 3 or 7.5? I don't know. Quantifying the rate of growth, putting a number to it, is going to be extremely useful for exponential growth because once things are numbers, you can see if these numbers are directly proportional to each other. But there is definitely a taboo around talking about rate of growth with students that are too young mathematically, because the rate of growth is called the derivative of the function, and it is a general consensus with which I don't particularly agree very much, that calculus is difficult and it shouldn't be taught to students early on because it's difficult. I absolutely disagree with that. I find it very difficult to teach functions without having the vocabulary of calculus, and this is the essential vocabulary. The rate of growth of a function is the derivative of that function. Here is some notation for the derivative of a function so that we can put that into equations if we want. So the defining characteristic of exponential functions is that the derivative is directly proportional to the function itself. Here is that same sentence written down with notation as an equation. I don't particularly like this symbol for something being directly proportional to something else. I don't think it's that common a symbol for people to use, so maybe it looks a little weird. So here it is written down in a different way. Something is directly proportional to something else when it is a constant multiplied by that thing, right? So the derivative of the function is equal to k times the function itself. If your function has that, that means that it is exponential. So I said earlier in this video that I don't think exponential functions are particularly a topic that students tend to say it's the most difficult thing. But there is one exception, and it's that whenever the teacher talks about exponential functions, they have to also introduce a very special number, which is the irrational number e, so that it can be used as the base of a very special exponential function, which is e to the power of x. And that whole thing is presented in an extremely mysterious way to students, which makes it difficult. The only thing that the teacher is able to say about the irrational number e at that point is, well, it is a special number, it is important, you'll understand it later. And the only thing that the student can do is say, okay, I guess. But it's not that the teacher is not willing to give a better explanation for that at that point. Is that the vocabulary to give that explanation has not been presented. So remember that I said that the word derivative means the rate of growth of a function, and that a function is exponential if the derivative is directly proportional to the function itself, with this constant k here. Well, if that constant k happens to be the very special number 1, and instead of being directly proportional, we are just saying that the derivative of the function is equal to the value of the function, that is what the number e represents. The definition of the number e is the base that the exponential function needs to have in order for this to be true. That is why this number is special. It's because of the way that it's defined, and it's defined in terms of the exponential function itself. It doesn't have a different definition that your teacher could say, oh, that is why this is special, so now let's use it in an exponential function. That's not the case. It is special because of exponential functions themselves, and your teacher is not able to explain to you why this is relevant or important without talking about derivative. Much later on in your life, when you actually are being taught calculus, there comes a point when your teacher is going to tell you what the derivative is for a bunch of functions. Here are some examples. And it again becomes mysterious. Like, why is the derivative of e to the power of x equal to e to the power of x? What is the explanation for that? And there is no explanation. This is the definition of the number e. So I might show you a proof of why the derivative of this is this or the derivative of this is that. But this, I'm not going to show you a proof. I am going to have this conversation that we are having right now. The derivative of the exponential function is itself by definition. And then if the constant happens to be a different number, k, it just becomes e to the power of kx, which, using the rules of exponents, becomes a different base, just like we were talking about before. So I told you that knowing this about the growth of exponential functions is going to help you recognize which contexts in real life should be modeled by exponential function. It's anything that is growing at a proportional rate to its current value. So the first two examples that come to mind are population growth and money invested in a bank. When I say population growth, it can be humans, but it can also be any kind of animals like rabbits or ducks or bacteria. Why is this an exponential growth? Well, it is because the thing is replicating itself, right? The rabbits are making more rabbits. The bacteria are making more bacteria. So if you start out with more rabbits, then they're going to make more rabbits than a smaller group of rabbits would make. So the number of new rabbits, which is the growth of the function, is proportional to how many rabbits were there in the first place making those rabbits. So that is a perfect example of exponential growth. And as a consequence of that, you're going to end up having something growing really, really fast because it's exponential. So that is why population growth is kind of a complicated topic, because you end up having rabbits taking over the world or something like that. And money in the bank grows exponentially as well, because the interest rates that the bank pays you is not a fixed amount of money per month. It's not like I'm going to give you $100 each month. No, it's a percentage. It's an interest rate. So they're going to see how much money you have, calculate a small percentage of that, which is proportional to the whole, and then give you that much again. So yes, money in the bank eventually grows really, really fast, which is always nice to know. But the decreasing functions are interesting as well. And the two most common examples of decreasing exponential functions that you're going to see in exam questions, but I mean that not in a cynical way, like we're only doing this to study for a test. They are very common in exam questions because they are really common in real life. So the first example of a decreasing exponential function that you're going to see a lot is radioactive decay. So you have a radioactive substance, I don't know, it's uranium or plutonium or something, and you know that that stuff decays, right? They emit particles or whatever, I don't know physics, but as they do, those particles consume its mass. So the mass of radioactive substance that you have tends to get smaller over time, and depending on the substance, that is going to take a long time, but the rate at which that happens depends on how much of the substance you have. If you only have a tiny little bit of radioactive substance, it's only emitting a small amount of particles, so its mass is decaying slowly. But if you have a huge amount of radioactive substance, then it's going to be emitting proportionally more particles. So those particles get out of the substance. So that is the rate of growth. Well, not growth, in this case, opposite growth, right? Decay. The point is that if you have more particles, then more particles are going out. So it's decaying faster. So it's directly proportional to the current mass. So it is exponential. And the last of the four traditional contexts that I want to tell you is coffee. Specifically, the temperature of the coffee, which is also decreasing. it has a horizontal asymptote on the right side in the end, because your coffee is not going to freeze no matter how long you take to drink it. It's just going to become the same temperature as the room. And again, I don't know physics, so I can't explain to you why it is this way, but the speed at which the temperature decreases is proportional not to the temperature itself, but to the difference in temperature between the coffee and the room, which is why this particular exponential function does require the vertical translation that gets the asymptote out of the axis and puts it here somewhere else. So those four are the typical examples that I wanted to share with you, but it's not difficult to find other examples, and you can search for them by yourself. Here, all that I did was to search for the word exponentially, and I clicked on news. I like to use that button because it will give me a variety of things. If I do the same thing again a week from now, I'm probably going to get different results because it's things that are in the news. So for example, the first hit that I got here says, how DNA molecules can exponentially self-replicate. Well, that's obvious, isn't it? Because they're replicating themselves. So the more molecules there are, the faster the amount of molecules will increase. So yeah, that's exponential. The fourth item on this list is less obvious and it's a little bit more funny. So pickleball is here to stay and growing exponentially. Let's think about it. Does it make sense for the number of people who play pickleball to increase exponentially? It kind of does make sense, doesn't it? Because if you start with a small group of people who like playing this game, and then these people start convincing their friends to also get into the game, that kind of has a feeling of exponential growth. The more people that are currently playing, not all of them are going to be enthusiastically bringing their friends, but some of them are, a fraction of them. So that is directly proportional. And then the exponential growth is going to happen. There was this other one that I found, and I kind of doubted it a little bit. Mexico's avocado sector shows exponential growth. That's not something that would kind of obviously be exponential, because it's not that the avocados themselves are planting more avocados. It's humans who are doing the planting, I hope. So it is an outside source of avocados. It's not proportional to how many you have right now, so it doesn't necessarily have to be exponential growth, although it can still be if those humans are working faster and faster in the appropriate way so as to make it look exponential. And it's perfectly fine to model a real life situation as an exponential function, even if it isn't a naturally exponential situation, so long as the numbers agree with you, which is not always true. When you see an article in the news, you see this word exponentially being misused a lot. So I went to check, and I underlined something in the article here because I'm going to use these numbers in a minute. So between 1994 and 2021, avocado production increased by 200%. I'm going to use this number. Just keep in mind that increasing by 200% means multiplying by 3, okay, not 2. An increase of 100% is multiplying by 2. You have what you had, and then that same amount again. Increase of 200% is multiplying by 3. So this article didn't have a graph of the avocado production in Mexico, so I searched someplace else. I found this graph, which the Mexican line is the one on the top, okay? But it's not exactly the same time frame. They had said 1994 to 2021, and I'm going to just ignore everything that comes before 1994 on this graph, but it doesn't quite go to 2021. It stops at 2012, like I've circled in the image. It actually has a little bit more. It's 2014. And I saw this picture. I'm just thinking, this doesn't really look like an exponential function, right? But let's give it a chance. So remember that times 3 increase from 94 to 21. So I just put this image in GeoGebra and I added an extra point to be 2021 according to that information, which is that point E that I marked in the picture here. Points C and D are just 2 points in the graph that I clicked to mark them as well. And then I used this command called fit that I've circled in red in the picture here. I'm not going to go through how this works right now, but I am going to link a different video that I have about a completely different topic where I do talk about how to use this command. So anyway, I asked it for a function that you can see. It's a times b to the power of x plus c, which is the exact same type of function that we were just talking about on the whiteboard before. And it gave me back this function, which it also put in the graph as this blue function. And what do you know? It looks really good. It seems to fit the data very well from 94 to 21. Of course, it doesn't fit the data well before 1994, but then again, nobody said that it would. So I was very pleasantly surprised to find that this time, at least, the news article was correct. I am not sure if they went through the trouble of actually doing this before they just threw the word exponentially in there, or if they just got lucky. But hey, then again, whatever works. But I just want to point out, though, that if you look at the expression for the function that GeoGebra is telling me that it plotted, it seems to be 0 times 2.16 to the power of x. And it clearly can't be 0, right? Because otherwise that function would just be 1.71, which would be a horizontal line. This can happen a lot in GeoGebra. It's just about significant figures. That is a small number that is not 0, but he's not showing me enough digits for me to see what the number is. So here I have made the calculation by plugging in the point e into the given expression for the function, but where I don't know the value of the parameter a, and then I solved for a. There you go. It is 0.004 something. The thing is that GeoGebra doesn't really use 3 significant figures. It uses 2 decimal places. And this is a nice example of why fixing a number of significant figures is a superior choice to fixing a specific number of digits. And by the way, this whole thing about the avocados could totally have been somebody's IA. Maybe I'll write it out later. I don't know if I'm going to have the patience to do that. But if I do, I'm going to link it in the description of the video. And if I don't, maybe you can do it and send it to me. But it doesn't always work that well, okay? This other one that I'm showing you right now is trying to do the same thing with different contexts from the news articles that I found. This had something to do with clean energy production or something. And notice how the graph is going until 2028, which we're not there yet. But the point of the article was that 2023 had an unexpectedly high value. So it didn't fit the previous predictions. And you can see that in the picture. 23 is much higher. So they were updating the predictions, seeing what's going to happen if the bigger number in 2023 represents an exponential growth that we weren't noticing before because we were still in the small numbers close to the asymptote. But I don't think it looks like that. I don't think it's actually going to be exponential. I think the graph that they produced is actually probably good because you see the type of growth that you were having in the previous years. It keeps going the same type of growth in the following years, and 2023 is just an outlier that had a really big growth. And the function that I plotted through those points, it is an exponential function because it is what I asked GeoGebra to do, but it doesn't really fit the data points very well at all. They did use the word "it's growing exponentially" though, which was not, in my opinion, as good of a use of that word as the avocado example, which if you thought the avocado IA was too short and you weren't sure if it was enough, maybe you could include this as a comparison. I don't know. Why do students think that it's hard to come up with ideas for IAs? Here's another one. How many rockets SpaceX has launched per year? The last bar is a projection. It's 2024. But the next to last bar is 2023, and it really does look exponential. I hope they do launch that many rockets. And speaking of rockets, last night after I thought I was done preparing all of the things for this video, I sat down to watch an episode of the show For All Mankind. Incredible show, really good. It's on Apple TV. I have nothing but good things to say about that show. But I was watching an episode last night and a character said the word exponentially. So I am going to show you a scene from the series. And just for a little bit of context, they have this base in Mars and they found this asteroid that is very rich in minerals or whatever. They want to bring the asteroid to orbit in Mars so they can mine the minerals and make a ton of money. But the concern of some of the characters is that it might not be good to do this mission at all because it is potentially worth a lot of money, the asteroid. But the thing that they're worried about is that it's going to take a long time for them to see that money because they're going to have to develop the equipment to mine the asteroid and then take things to Mars to build the equipment and all of that. So they know that there is a lot of money to be made, but they're not making it fast enough. And somebody else suggests, hey, why don't we just bring the asteroid to Earth instead? I think that's a terrible idea, but anyway, I haven't watched what happens next yet. Their point being that where the asteroid is going to impact the speed at which they see the return on their investment. So they wanted to say something like this: depending on where your asteroid is, this is the speed at which you can get your money. And they wanted to say an exponential increase.
Bringing the asteroid to Earth instead of Mars, mining it in orbit here.
Using the existing helium-3 infrastructure
from the moon would allow us to start mining it
right away.
And not having to send thousands of vehicles to Mars means a faster timeline.
And an exponentially faster return on investment.
But that doesn't make any sense at all. They don't have a function with an independent variable and a dependent variable to compare. They just have 2 points. The asteroid is either in Mars and gives a slow return, or it is on the Earth and brings a fast return. That is just 2 points. That is not a function. You cannot say that this is exponential. It's not even a function. Okay, so that's all that I wanted to say. Here is some homework for you. Do the avocado thing. Not with avocados, of course. Go find something, some source on the internet that uses the word exponentially, and study it a little bit. Decide whether or not it makes sense to use the word exponentially in that context. If you have the patience to write it out, link it in the comments. I would love to see it.